I'm Donna Cossum. I was a PhD student at Leiden Observatory, which is where this research was performed, and now I am currently a postdoc at NASA Goddard Space Flight Center. And today I'm going to present results on the experimental evidence for interstellar methane ice formation in the water-rich ice phase of molecular clouds. So as you know, near the beginning of the stellar formation cycle, a molecular cloud is formed. At the edge of the cloud is noted as the translucent phase. So this phase is characterized by relatively low densities, so about 10 to the third hydrogen molecules per centimeter cubed. Because of this low density, there's still a fair amount of external UV radiation present, but the density is high enough to allow the conversion of ionized species to neutral atoms. So in this phase, neutral atoms are present in the gas phase and then accrete onto cold dust grains. When they accrete onto these grains, they react, mainly form water. Other molecules or other atoms such as nitrogen and carbon also accrete and are constrained for the most part to be hydrogenated to form ammonia and methane respectively. In addition to the formation of simple hydrides, recent laboratory work from our group in Leiden has showed that this water-rich ice phase may also contain more complex species. So from a bottom-up perspective, simple species like acetylene can polymerize to form polyions, and to make it more complex, a methyl group can be added to form methyl polyacetylene. Such species can then accrete onto carbonaceous dust grains that were formed from the nucleation of PAHs. In this study, we just focused on the simplest representative of methyl polyacetylene, which is methyl acetylene, also known as propyne. So in this work, we showed that propyne can react with nearby OH radicals to form an assortment of alcohols. So the paper is called Alcohols on the Rocks. As you go deeper into the cloud, the density increases to about 10 to the fifth, the temperature drops, and external UV radiation is largely shielded. In the gas phase, a lot of the remaining carbon has now been converted to carbon monoxide. This carbon monoxide will eventually freeze out on top of the water-rich ice and will be hydrogenated to form formaldehyde and methanol, as found in a number of independent investigations. This CO hydrogenation pathway can also lead to the formation of more complex organics. If you continue to bombard CO and H, you can form glycerol, which is a necessary ingredient for glycerophospholipids, which are what modern cell membranes are composed of. So the glycerophospholipid bilayer makes up the cell membrane, and then the glycerophospholipid itself has glycerol as the backbone. And then if you continue along this formation pathway, you could even form ribose, which is an essential component of RNA, for example. So these species that are formed in the ice can then potentially be transferred to the next stages of star formation and or influence the chemistry in those stages. So some of the big questions that we still have, for example, are when these molecules are released into the gas phase during the warm-up period, do they engage in further reactions, and to what extent? What fraction of these molecules is inherited by the disk? And then an even more fundamental question, are these molecules essential for chemistry on the early Earth? So if we want to better understand our origins, it's important to investigate the formation of molecules in interstellar clouds that we may have potentially inherited. So the most abundant ices that have been detected towards the interstellar objects are shown here. So the most abundant one is water, and experimental investigations support its formation from atomic O and H. CO2 is predominantly formed from CO plus OH. So CO and OH combine first to make the HOCO intermediate, so HOCO, and then breaks apart to CO2. CO is a gas phase species. Methanol is formed from the hydrogenation of CO ice, and ammonia is formed from the hydrogenation of N. But what about methane? So observational constraints show that methane should be formed from the hydrogenation of C in the water-rich ice phase. But to date, this was not experimentally proven. So if it wasn't experimentally proven, how do we know that this can actually happen? So the closest experiments that have been performed were reported in 1979 and 1998. And although these laboratory experiments pioneered the field of laboratory astrochemistry. But on the other hand, they were performed under water-poor conditions and also did not start from a beam of ground state atomic carbon in which the fluxes were calibrated for. So this then leads to the question, well, why hasn't the solid state formation of methane starting from atomic C and H in a water-rich ice been pursued, especially since methane is one of the most abundant ices to be detected? You would have thought that this would have been a priority. And this just comes down to the fact that it's technically challenging to simulate carbon atom chemistry in realistic interstellar ice analogs. To do this, you would have to couple an atomic carbon source with more favorably an ultra-high vacuum setup, which can be quite risky. And so that's what we did here with our ultra-high vacuum setup called SurfaceIDE, which stands for Surface Reaction Simulation Device. And this setup allows us to study non-energetic processes at the low temperature of 10 Kelvin. And here, non-energetic refers to a radical-induced process that does not involve energetic particles such as UV photons or electrons, for example. So this non-energetic process is what we expect to be one of the more important processes to how simple and complex organic molecules are formed in these cold, dark, and particularly in these dense clouds. So we have a newly installed atomic carbon source, and the way this works is that we have a tantalum tube filled with carbon powder. And so this tube gets heated, and carbon then sublimes and reacts with tantalum to form tantalum carbide. So this essentially breaks apart molecular carbon into atomic carbon, and then the atomic carbon will continue to diffuse through the tantalum and be released into the gas phase. We have a hydrogen atom beam source that produces hydrogen atoms by thermally cracking hydrogen molecules. We also have a microwave atom beam source that allows us to produce hydrogen atoms as well as nitrogen and oxygen atoms. We have two independent dosing lines that are turbomolecularly pumped. Cryostat is used to cool and heat the sample, and this is where also the ices are grown. And then we have all the analysis is performed by a quadrupole mass spectrometer and a Fourier transform infrared spectrometer. So the two techniques that I use are temperature programmed absorption, also known as TPD, and reflection absorption infrared spectroscopy, also known as RARES. So with TPD, I'm able to measure the mass of the desorbent species as a function of temperature. Since molecules have characteristic desorption temperatures, this is just one way that we're able to identify the species formed. So as the molecules enter the QMS, they get bombarded by typically 70 eV electrons, which can then fragment the molecule. This fragmentation pattern is then a fingerprint of the molecule formed. And then with RARES, I'm able to get the vibrational signature of the species that are formed in the ice. And this vibrational spectrum can then be recorded as a function of temperature, which can then be linked to the TPD data. All right, so two different types of experiments were performed, one without water and one with water. Since methane is observationally constrained to be formed also when water ice is formed, there may have been a short period when methane was formed just before water ice. So we wanted to see if that was experimentally possible. And then of course we wanted to see if methane could be formed in a water-rich ice as it should be in space. It's important to note that in the water experiment, water was deposited rather than being formed, and that's because we just wanted to disentangle the methane formation route. So water deposition is not meant to simulate the accretion of water on interstellar dust grains, but rather this is just used as an experimental tool. The hydrogen flux is an order of magnitude higher than the carbon flux, which is meant to represent the overabundance of hydrogen compared to carbon in interstellar clouds. And a methane to water ratio of 10% was chosen as this value has been measured towards some low mass young solar objects. So these panels show the rare spectra of the CH bending mode of methane, which is the most intense vibrational mode of methane. So these were recorded after 720, 1080, and 1447 with deposition in the two experiments. So you can see that this really just took a matter of minutes to acquire a pretty good signal to noise data. And then for extra confirmation of methane formation, the left panel shows the isotopic shift of CD4 when D is substituted for H, and the right panel shows the presence of the weaker CH stretching mode of methane. So it's quite clear that in the water-rich ice experiment, more methane is actually formed. Under our experimental conditions, the rate of formation was about twice as high compared to the experiment without water. So one of the concerns that we had was whether water would block C and H from meeting each other in the ice. To some extent, water probably does block C and H. However, this seems to be overpowered by the fact that water increases the residence time of hydrogen in the ice, and this may be partially due to the increase in the sticking coefficient and binding energy of hydrogen, and also water provides a larger surface area for hydrogen to absorb to. So there's actually more hydrogen available to react with carbon than if water wasn't present at all. So after a series of control experiments, which are not discussed here, we find that this is the dominating mechanism to methane formation in our experiments, which supports observational studies that methane should be formed in the water to ice phase of interstellar clouds. Now, in the interstellar medium, the methane-water correlation will most likely be set by the availability of the simultaneous accretion of CH and O. But because there is more water than methane, I think it should be taken account into models that C and H are expected to react with each other in the growing polar ice. So to put this work into a larger context, radiation chemistry in the gas phase is needed to provide ample C, N, and O atoms. These atoms accrete and react to form the simple hydrides. These simple molecules can then break apart and recombine to form larger species, or they can remain intact and then be transferred to the next stages of star formation. So for example, Titan's atmosphere is thought to have inherited some of its methane from the interstellar medium. Taking into account the C atom channel in addition to the N and O atom channels will be important to put the present findings into a cosmochemical context. And this is especially timely with the JWST. Cycle 1 proposals were just turned in. The JWST will be, so methane, because of tellurics, methane is difficult to probe with ground-based telescopes. So the JWST will be a desired facility to detect methane ice, particularly since high sensitivity is needed if you want to detect methane in these quiescent cloud environments. All right, and thank you very much for watching my talk.